I think it's me. You're
Ah,
waiting for Nick? Yeah,
yes.
that's me.
Okay. Okay. Good. Yeah, I didn't know.
Yeah.
I was expecting. All right. Good. So everyone is here, so we can start. So let's start. Uh, all right. So welcome to the third day of Random. Our first speaker is Kwon-Jun An from MIT. Can you share your screen? Okay.
Okay. Can you guys hear me well?
Yes.
Okay. Okay, so let me begin. Hello, my name is Kwon-Jun An, graduate student at MIT. And today I'm going to briefly talk about my work on simpler strong refutation, random KXOR. Given the time limitation, I won't be able to go into great detail. So for the details, please refer to the full version of this presentation. So let me first describe this random KXOR model for those who've never seen this before. So given n binary variables, x1 through xn, we randomly sample n random KXOR constraints. So each constraint is on KXOR constraint consisting of k randomly selected variables. So just give you some examples. For k equal 3, the constraints will look like these. So in general, when you consider other predicates than XOR, it's actually called a random CSP, constraint satisfaction problem. So these CSPs are in general are well studied because of interesting phase transition phenomenon. So if you draw a plot with this density defined as m over n, there's a threshold such that below the threshold, the random model or constraint are satisfiable with high probability, and above the threshold, it's unsatisfiable with high probability. So these are existential results, and algorithmically, you might want to ask, can we find a satisfying assignment for those regime below the threshold? And can we find a proof of unsatisfiability above the threshold, namely refutation? Just like my title shows, this work will be focused on this refutation problem. And refutation problem is a fundamental question with many applications in cryptography, hardness of learning, etc. And following the work, famous work by Allen, O'Donnell, and Widmer, we focus on XOR. In fact, refutation for other predicates can be reduced to strong refutation of XORs. So you might then wonder what strong refutation is. So for the same model and in the same plot, actually, if you're more above the threshold, you can hope for strongly the regime falls in strong unsatisfiability regime, which means that for any assignment, the fraction of satisfied constraints is concentrated around its mean, which in this case will be half. So in this strongly unsatisfiable regime, the refined algorithmic question is to find the proof of strong unsatisfiability, namely strong refutation. So let me then go over briefly the literature, existing algorithms on strong refutation. So drawing plot between density and the computational complexity. So if you're in the strong refutation regime, you can obviously just check 2 to the n different binary assignments to just brute force guarantee this strong unsatisfiability. So there's this obvious 2 to the n algorithm. And then you might ask what you can do in polynomial time. So these previous works have shown that if you're somewhat way above the regime, looks like this, then there's a polynomial time algorithm based on spectral method. So as you can see, there's a big disparity between what you can do like with brute force 2 to the n algorithm and with a polynomial time algorithm. And you might ask then what happens in between. And recent work by Raghavendra Rajshram, they were able to actually interpolate between these two regimes, bridging this gap by coming up with results like this. So concretely, for this density, they show that there's a sub-exponential algorithm runs in time like this. So this is indeed really beautiful and interesting results. But actually, their results relies on some elaborate analysis. In particular, they construct some complicated matrix and analyze the spectral norm of that matrix, and require some elaborate like counting technique. And also on top of that, it turns out like the naive approach to this doesn't quite work, and they need to actually pre-process and also post-process their algorithm to make it work, which comes with additional like analytical complexity as well as just algorithmic like complication. So this work in a nutshell is about simplifying their spectral norm analysis. In particular, my analysis is based on more elementary counting arguments. And more significantly, it captures the difficulty more transparently. And by just noticing the main challenge of this approach, I was able to elegantly just rescale the algorithm. It's kind of obscure term right now. But so that for even k, I could come up with a simpler approach. So this is a really rough overview or summary of what my work is about. So if you want to see some details, please ask me or refer to the long version of this presentation. Thank you very much.
Okay, thank you. So let's open the floor for question. If you want to ask a question, you can unmute yourself and please ask.
I have a question. Thank you for the talk. Does this extend to other CSPs? Or is it special for XOR?
For the question, so other CSPs, as far as I know, from the work by Ellen O'Donnell Whitmer, they show that refutation of other CSPs can be reduced to strong refutation of XORs. So leveraging that reduction, you can show other reduction, other CSP refutation. Yeah.
Thanks.
Thank you.
Can you say a little bit about the ideas that allow you to do this simplification? Like what new ideas you?
I see. So I was trying to just extract the like core idea, but it's really hard to like extract like the main idea. But at a high level, their counting arguments like relies on like counting via like making an analogy to like probability. But then what I figured out was just defining some right notion. The counting becomes way simpler because it just becomes like the counting of like valid partitions, and I found it like much easier, and it actually captures like the how like the term like quantity depends. So yeah, it's really hard to say like at a high level how like the simplification occurs. Sorry.
Any more questions? Maybe another question is, are there like matching lower bounds to these upper bounds, like in the restricted models?
As far as I know, this result by Raghavendra Rajlam, there's like kind of SOS lower bound to the result. So it's within that class of algorithm, the result is optimal. But for like general class of algorithm, like lower bound is not known as far as I know.
Right. Yeah. Okay. Good. Thank you.
Thank you.
All right. So let's move on to the next talk. So next we have João Ribeiro from Imperial College. You want to share your slide?
Yeah.
He's going to talk about extractor lower bounds.
Okay. Yeah. Thanks for the introduction. So this is joint work with Divesh Agarwal, Xiao Guo, Maciej Abramski, and Noah Stevens-Davidowitz. And the topic of our work is randomness extraction, which is the art of converting weak sources of randomness into nearly uniform or perfect randomness, which is fundamental for many applications. And the starting point for us is what we call the probable extraction task, where we start with a weak source of randomness X, which is a K source, meaning that it contains at least K bits of mean entropy. And the goal is to design an extractor, X, with D seeds, such that for each fixing of the seed 1 through D, you output the block y1 through yd as a function of x. And the goal here is that we want that at least half of the blocks should be close to uniform in the sense that the statistical distance between the distribution of the block and the uniform distribution is at most some epsilon. And tests of this type show up, for example, as important steps in constructions of several multi-source extractors. And there the bottleneck is really the number of seeds that you need for probable extraction. And so if you can do probable extraction with fewer seeds, then you can improve the parameters. You can also simplify the constructions. And so in this work, we try to understand what is the minimum number of seeds that you need for probable extraction. And what we found out is that, starting with this question, we end up looking at some natural variants of extractors, and that studying them requires developing new lower bound techniques and leads to many surprising results. Okay, so just to get started, let us look just at the naive solution for probable extraction, which is actually used in all previous works, which is to simply plug in a strong seeded extractor, which is a special type of extractor with many applications, with the property that the expected statistical distance over a uniform choice of the seed is small. So in order to understand the limitations of this naive solution, we can ask what is the minimum number of seeds for strong extractors? And this turns out to be a well-studied question. So it is known that the minimum number of seeds scales like n minus k over epsilon squared. So the upper bound comes from the probabilistic method, and the lower bound is due to Radhakrishnan and Tashma. However, this doesn't really characterize the minimum number of seeds for probable extraction. It only gives an upper bound. And probable extraction actually is equivalent to designing a seemingly much weaker type of extractors, which we call probable extractors, and they satisfy the weaker requirement that only less than a delta fraction of the seeds should lead to statistical distance larger than epsilon for any k source. So now the question of the minimum number of seeds for probable extraction is equivalent to asking about the minimum number of seeds for probable extractors. And it turns out that in this case, we don't have good bounds that are independent of the output length. So they are trivial for small output lengths, which is very different from what we have for strong extractors. And so in this talk, and actually in the paper, we focus mostly on the most basic probable extractor, which we call a somewhere extractor. And this corresponds to setting delta equals 1 in the definition of a probable extractor. And it amounts, so basically somewhere extractor has only the very weak requirement that the minimum statistical distance over the choice of the seed is small for every k source. Okay, so the question, so what we're trying to see here is whether somewhere extractors fundamentally require significantly fewer seeds than strong extractors. And I'll just briefly discuss our results, comparing them to strong extractors. So for strong extractors, we have an optimal upper bound of n minus k over epsilon squared, and this is given by the probabilistic method. And actually, the probabilistic method is actually optimal for getting constructions of many different combinatorial objects. And we can also see that the probabilistic method gives the same upper bound for somewhere extractors. And in our work, we also prove that you cannot do better than that with the probabilistic method. However, quite surprisingly, we give an upper bound that actually beats the probabilistic method in some regimes. And it also gives a fundamental separation between strong and somewhere extractors, because we also know a lower bound of n minus k over epsilon squared on the number of seeds of any extractor. So number of seeds of somewhere extractors scales like roughly like 1 over epsilon. For strong extractors, it scales like 1 over epsilon squared. And to complement our upper bound, we derive a lower bound of n minus k over epsilon on the number of seeds of any somewhere extractor, which also carries over to all probable extractors. And deriving this lower bound requires the development of new lower bound techniques. So we develop a new general framework for lower bounds. And as a bonus, we also apply this general framework to strong extractors, and we also get an alternative simple proof of the optimal lower bound for strong extractors. Of course, there are still many open questions. So for example, can we get an optimal upper bound of n minus k over epsilon on the minimum number of seeds for somewhere extractors. We believe this to be the case, but we just haven't been able to prove it. And to kind of complement that, can we get explicit constructions of somewhere extractors with parameters that beat the optimal strong extractors? Okay, so before I wrap this up, I'd just like to briefly describe our new approach towards lower bound. So starting point, I mean, is very obvious. So the way we want to design a lower bound is that for each extractor, we want to design a distribution P over this output set that is bad, in the sense that first, P is sufficiently biased, and the notion of biased will depend on the type of extractor that we're considering. And second, P is the output distribution of some K source X. So if we have these two conditions at the same time, we can basically immediately get a lower bound on a number of seeds. But the problem is that satisfying both of these conditions at the same time is kind of difficult. So our main contribution here is that we identify an equivalent statement to condition number 2, which morally states that if we define P as a function of this distribution, special distribution A, which is the output distribution of the extractor on a uniform input, then it's very easy to verify whether condition number 2 is satisfied, which gives us more freedom to try to also satisfy condition number 1. And this is the kind of the general framework that we apply. So we design P always as kind of a scaling of this distribution A. So for example, if you're dealing with somewhere extractors, then P will be a scaling of this special distribution A with a biased product distribution, and then the proof just follows by Fourier analysis. And if we're dealing with strong extractors and you want to get the optimal lower bound, then we take P to be the restriction of this distribution A to a small Hamming ball with a carefully chosen center. So yeah, so this is everything. Yeah, thanks for listening.
Thank you. Now we have time for questions. So I'm opening the floor. You can unmute yourself and ask a question.
So I have a question.
Mm-hmm.
So can you say something about why your upper bound among this 2 to the power n minus k, which seems very bad? And can you say something about why the probabilistic technique fails to give you n minus k?
Yeah, I mean, so the reason why it fails to give n minus k over epsilon, really, I mean, okay, so our upper bound is actually not probabilistic. We give a construction of a somewhere extractor with this number of seeds. But I mean, the reason why the probabilistic method doesn't work really is that, how shall I explain this? When you look at the, you look at these strings as these d-bit strings. If you look at the strings with low weight, so you define a source over strings with low weight. This will be a k source, and this will kind of kill your random function as a somewhere extractor. So that's why you cannot get. So as soon as your number of seeds goes significantly below n minus k over epsilon squared, you cannot get a somewhere extractor because of that. Yeah, but I'd just like to add, of course, that I mean this upper bound really only improves on the probabilistic method when your mean entropy k is very high, right? So when it is like n minus a constant.
I have another question. What about lower bounds for non-strong extractors, right? So we can also
Right, yeah, so the lower bound of n minus k over epsilon squared also applies to non-strong extractors. But yeah, our framework, or at least the results we get, really only apply to strong extractors.
Okay.
Yeah.
Thank you.
Yeah, but that would be very interesting. I mean, that's kind of going, going from it's like going to the setting of convex combinations, right? It's like you could allow somewhere extractors to output, a convex combination of, somewhere random sources.
Right.
And in that case, like our framework as it stands doesn't work, but we believe that it could be a starting point to get lower bounds for that as well.
Okay, thanks for answering the question. Right, so maybe it's time to move to the third speaker, So, okay, can you unshare your scene?
Yeah,
Okay,
sure.
good.
Thanks.
Thank you. So now, next we have Jonathan Mushairo, who's currently a postdoc at CMU. He's going to talk about list decoding, list recoverability of random linear codes.
Hi, can you see the presentation right now? Okay, great. Yeah, so thanks, Avishai. This is a joint work with Venkat Guruswamy, Ray Lee, Nick Resch, Shashwat Silas, and Mary Wooters. We have a few results. I'm going to focus mostly on one of them. So we're talking about codes. Binary code is just a subset of f2 to the n. And the rate of the code is the log of its size over n. It basically just tells us how many code words are there. And we generally like our codes to have high rate because that means we're more efficient to use. On the other hand, having a high rate makes the code less resilient to errors, which produces some trade-off, which is very widely studied in coding theory. Our noise model is going to be that we fix some p. And we assume that when Alice sends Bob a message, then some adversary is allowed to flip a p portion of the bits in the message that Alice is sending. And finally, this work focuses on a particular construction known as random linear codes. So random linear codes are a very basic, very important construction in coding theory, and essentially just means that our code C is going to be the kernel of some random matrix, where the dimensions of the matrix are chosen so that with high probability, the rate of the code is going to be the R that we want it to be. Okay, so here the red dots represent our code words. And I've taken a random linear code of some rate R, where R is pretty small. It's below what's known as the GV bound, which is 1 minus the binary entropy of 2p. And in this case, it's very likely that we have the following situation. It's very likely that every Hamming ball in f2 to the n of radius p contains at most one code word. And that means that we have unique decoding. Unique decoding means that if Alice sends a message to Bob, then Bob is able to uniquely determine what's the message that Alice was trying to send, which is great. On the other hand, as I said, the rate here is pretty low. So let's try to crank it up and see what happens. Let's take the rate up all the way to here. Okay. So now I've taken, now I'm looking at the code of a much higher rate. The rate is now larger than what's known as the capacity of the channel, which is 1 minus the binary entropy of p. And in this case, it's actually guaranteed. I mean, it's not even probable. It's guaranteed for any code of this rate that we're going to have a Hamming ball of radius p with an exponential number in n of code words, which means that Bob is really clueless as to what Alice is trying to tell him. So that's not too good for communication. So we'll need to tone it down a bit. And now I've taken R down to this middle ground between the GV bound and the capacity. And what happens in this middle ground is interesting. So let L denote the maximum number of code words in a Hamming ball of radius p. So on one hand, L is likely to be larger than 1. So we're not going to have unique decoding. On the other hand, L is very likely to be bounded by some constant that depends on R but not on n. So we can think of L as being pretty small. And that means that while Bob is not able to uniquely determine what the message Alice is trying to send, he does get a list of size L of candidate messages. And he knows that one of them is the correct message. And this is known as list decoding. So while not as powerful as unique decoding, list decoding is still a very prominent and useful notion in coding theory. And what we're going to study now is the size of this L. So we fix R to be epsilon below capacity. And we want to ask, what is L as a function of this epsilon? And this has actually been the subject of a pretty long line of papers which gave different bounds on this as a function of epsilon. And at least for the case of a binary random linear code, I think I can say that we pretty much settled this question in this paper. So here's our results. We give a lower bound on L, which essentially says that L is at least the binary entropy of P over epsilon plus 1. And this is nice because the recent work by Lee and Wouters gives matching, like an almost completely matching upper bound of and the binary entropy of P over epsilon plus 2. So up to 2 values, or sometimes, rarely, 3 values, we know the exact value of L that we accept for a code in this regime. Finally, I want to say a bit about the proof method. So in order to describe our main tool, how does one go about proving that a given code has L equal to at most K? So what do you need for that? You need to have a ball containing K code words. So you need to have K code words that are all close, at most P close to some joint center. So we call such a set of K code words a bad set. And what we basically need to prove is that a random linear code above a certain rate is likely to contain a bad set. And this brings us to a recent work by Resh, Rontzvi, Silas, Wouters, and myself, which analyzes something more general. This work talks about local properties of codes. And I'm not going to define what's a local property, but it's just enough to say that containing a bad set is a local property. So what this work says is that if you want to plot the probability that a random linear code of a given rate R satisfies some local property as a function of R, then this graph is going to have threshold behavior, which means that up to some rate, which we call the threshold, is going to be very, very close to 0. And then abruptly, it's going to rise up and become very close to 1. And another thing that this work does is characterize the threshold in terms of certain first moment inequalities, which essentially reduces the question of when is a bad set likely to occur to these first moment inequalities, which we study in the current work. And finally, I leave you with this slide, which just gives more details of all of our results in this paper for, I know, the coding theory people out there. Thank you very much.
Thank you, Anton. So we have time for a couple of questions. So in all these results, there's no dependence on n, right? So the least size.
Yeah, generally this is, yeah, the idea is that n always goes to infinity and all the rest of the things generally do not.
What if we are okay with polynomial dependence on n?
So, I mean, for the list size, it doesn't really matter at this point. I mean, right, so what can depend on n? If you allow the list size to depend on n, well, we just don't need to in this case, right? Because we know that as epsilon approaches capacity, it's going to remain some, I mean, it's going to depend on it has some linear dependency in epsilon until epsilon reaches until you reach the capacity, and then it's going to be exponential in n. So no real need to be polynomial in n unless you maybe you go into very, very particular resolutions just around the capacity.
Mm-hmm.
Okay.
Very good. Any more questions? Yeah, it seems that you settled this question completely. So do you have a natural open question now that you?
So one natural open question would be about what do you do? I mean, so there's also a result here. The lower bound that we proved also applies to non-binary codes, but there we don't have a neat matching upper bound. We do have some upper bounds, but not like something that closes it completely, and would actually be very interesting to do that.
Great.
Yeah.
I
Thanks.
have a quick question, if you don't mind. So this is for random codes. Could you say something about some pseudo-random property that would give you the same type of bounds?
I could, probably not in these few seconds, but I guess the important thing is what kind of codes satisfy this threshold phenomena that I talked about in the previous slide. And that's a very good question, which I'm actually thinking about right now. But I don't know, tell you.
All right. Excellent.
Okay. Thanks.
So maybe let's move on to the final speaker of this session, Aditya from UIC.
Hi, is everything, am I audible?
Yes, good.
Okay, so I'm going to start, okay? Okay, so hi, I'm Aditya. I'm going to talk about the list recoverability of randomly punctured codes. So this is joint work with Ben Lund, who was essentially just starting his postdoc at the Institute for Basic Science in South Korea. Okay, so first I'll define what list recoverability is. So here's Alice and Bob. So Alice has a message that you want to send Bob, and there's a channel which has some corruption. So this symbolizes corruption. So how error correcting codes are designed is that Alice encodes the message into a code word which happens to read code word at this point, and when you send it to the channel, there will be some corruption. For example, the D has become B and O has become A. But these codes are designed in a way that when Bob sees this, it's clear that this is the only way that this could have happened. So when Bob decodes it, Bob gets the same message that Alice intended to send. Okay? So it's a slightly different setting now. So again, Alice wants to send Bob a message, diligently encoded using some error correcting code. But now the point is there's a lot more corruption in the channel. And so what Bob sees is essentially this: like you can't even read the alphabet. But you know a list of possibilities for each alphabet. Like the first alphabet is one of C, P, or N. The second alphabet is either A, O, or L. You have a list for each alphabet, and it might so happen that so the ith column is the possible values for the ith code word, and it might just happen that Bob can spot this particular pattern and say, this must have been what Alice sent, so this must have decoded to code word. The point is Bob can also spot other patterns, like you can spot pandemic, you can spot something like Zoom call. So I guess so. The whole idea is to deal with this kind of errors, but you're still okay as long as there aren't too many possibilities for this output list, what's called the output list. So as long as the output list is small, there's still some kind of communication is possible. So that's kind of what list recoverable codes are. So here's what formally. A query code is said to be row, little l, capital L list recoverable if for every set S1 to Sn of the alphabet, these are input lists. If all the input lists are small, the number of code words that differ on at most some row and fraction of errors from the S1 cross S2 cross Sn is at most capital L. So little l is the input list size, so the list of possibilities for every alphabet, and capital L is the output list size, so the overall the number of things that you can possibly find in these things. Right? So even the case when row is 0 is very interesting, and that's called the zero error list recoverability. Okay, I'll just restate what the definition is. So it's little l comma capital L zero error list recoverable if for every set S1 to Sn of the alphabet of input lists of size at most little l, the number of code words contained in S1 cross S2 cross Sn is at most capital L, right? So I'm stating this as a communication problem, but of course, like these are, as with most code, these are very general combinatorial objects that come up in many different places. So for this talk, I'll just be focusing on the coding aspect of it. Okay. Here's a bit of definition. It's a punctured code. So let C be a query code and M be a set of indices. An M punctured code denoted by CM is just, you take every code word in C and just write down only the indices that are given by M. So this is an M punctured code. So every code word in C M is a substring of some code word in C. Okay, and here's an example. This is really a running example throughout. So Reed-Solomon codes. So you have some subset of the field, and a degree D Reed-Solomon codes with evaluation set M is the evaluation of all polynomials of degree at most D on those points given in M. So that is the degree D Reed-Solomon code with evaluation set M. And so so Reed-Solomon codes in some sense can be thought of as punctured codes. Okay, so here's the main result, and like slightly informally, fix any alpha. The alpha is like 0.001, like a very small constant alpha. Any QRE code of distance at least 1 minus 1 over q minus epsilon square can be punctured to rate something like epsilon over log q, so that it is list recoverable from constant fraction errors and list sizes 1 over epsilon squared. So and the output list is almost the same as the input list. So again, so to put this all in the example world, so here's a corollary. There are Reed-Solomon codes of rate epsilon over log q that can be list recovered from, again, a row is a constant fraction errors of list size at most one, at least 1 over epsilon square, and the output list almost close to the input list. Okay. So, right, and a random puncturing of this rate does it with high probability. And so, what is one way to interpret this? So this is a corollary. So that, again, there are Reed-Solomon codes of rate epsilon over log q that you can list recover from lists of size 1 over epsilon squared. Okay, so here's a very well-known result called the Johnson bound, which says every Reed-Solomon code of rate epsilon over log q can be list recovered from lists of size something like 1 over epsilon log q. So here the quantifier is that there are Reed-Solomon codes. On the other hand, here's a bound that says every Reed-Solomon code has some guarantee on list recoverability. So I guess one of the main points is that there are Reed-Solomon codes that are list recoverable beyond the Johnson bound. And by beyond the Johnson bound, I mean you can list recover them from like larger list sizes than the Johnson bound. So that is a main result. And that's all I'm going to say. I just want to talk about the open question. So what is left? And here's a question of Guruswamy. So, okay, there's a question star because the original question of Guruswamy was stated in the language of unbalanced expander. So this is really the same question stated in the language of list recoverable codes. So fix D and epsilon. So really D is 1 is okay and epsilon 0.1 is okay. So fix D and epsilon. What is the smallest m such that a random m puncturing of the degree D Reed-Solomon code is list recoverable 0 error with a list of size something like q, the field size. Again, so D is so an m puncturing means like let's take a random subset of m points and just that is a puncturing. So this is a question. Again, so this is a conjecture. I mean, it's written in the paper. I'm sure this was known as folklore, but we wrote it in the paper anyway. And here's the lower bound, which also I'm sure is folklore, but it's in the paper anyway. So, and what's new is that the upper bound is actually something like square root q, and before this, nothing better than q was known. So it's not quite log q, but it's somewhat better than q. And so that's all. Thank you. Is there any questions?
Thank you. Yeah, right. So again, I'm opening the floor for questions. You can unmute yourself and ask a question.
Sure. Can I ask a quick question?
Yes.
So in your result, you puncture down, if I saw it correctly, to epsilon over log q.
Yeah.
So for Reed-Solomon codes, q is always at least the block length, right?
Yes.
So can you get anything if you want to puncture down to constant rate, or can you only beat the Johnson bound sort of in this sub-constant rate regime?
Right. So it's only in the sub-constant rate regime as far as the rate needs to be less than log q, much less than log q for this to mean the Johnson bound, as far as I know, with respect to this result.
Okay.
So I have a question. Is there a matching lower bounds for your technique, meaning that the parameters cannot be improved?
Oh, I don't even know that. So for example, like Reed-Solomon codes, I said it should be 1 over log q, right? I don't know if, I'm not sure if the geometry is relevant of Reed-Solomon code. I don't know if any code of the similar rate cannot be done.
But the more general theorem says the result for any code. So
right,
can
yeah.
you show that, there are codes where you cannot get better than that?
I don't know. Yeah. So and really in the regime I'm not thinking about, it's not even clear. So, I mean, if I had to, I would conjecture it shouldn't, every code of like small enough rate should be punctured much beyond better than this, but I don't know.
Okay. Thank you.
Yeah, actually, if I could ask one more question. So at the end, you sort of mentioned the connection, I guess, to the unbalanced extractors. So are you sort of, sorry, unbalanced expanders, yes, exactly. So are you sort of thinking kind of as a motivating application for improving the list recovery of Reed-Solomon codes, kind of an improved construction? Because I guess, and if that's the case, could you say something about like the Parfresh-Vardy codes, which were used in like the GUV paper?
Right. So again, so there are codes that are much list recoverable with much better parameters, and they have been used in the construction of unbalanced expanders. But the point is, right, so this looks like a very nice geometry question that should be either should be doable, and so that was where my main motivation came from.
I see. Okay.
Okay, so I want to thank all the speakers of this session. I really enjoyed all the talks. So thank you. And I guess we'll take now a break for 20 minutes. I will leave the